Yeah, so in our last class, we started talking about auto transformers. What is auto transformer? Basically, a transformer with one coil only. Okay, so this is somewhat similar to a resistive potential divider, but the main difference is that a potential divider cannot increase voltage, whereas auto transformer can also increase and can also decrease voltage. Okay, yeah. So today, let us start with a problem, one question related to auto transformer. The question is as follows. So we have a 10 kVA 2200 by 110 volt two winding transformer, two coil transformer, and this is connected as an 2200 by 2310 volt auto transformer. Okay, find the kVA rating, that means maximum kVA that can be handled, by this reconnected auto transformer. Okay. What does this question mean? It means it's like this. Suppose I have a transformer, normal two winding transformer. Okay, here is one winding, suppose this is the 2200 volt winding, and here is another winding. This is the 110 volt winding. So this is a normal two winding transformer, but we have to reconnect this to use it like a auto transformer, and so that the voltage rating of the auto transformer becomes this 2200 by 2310 volt. How to do that? First question, how this reconnection is to be done. Okay, even before that, we have to look at the dot convention, dots for these two coils. So how should the two dots be here? If I put one dot on the upper side of this coil, then the other dot, if you find it, you will get it on the upper side of the other coil. Okay, now, so at any moment, if this voltage here is 2200 plus minus this volt, then at the same moment, here this voltage will be 110 volt. Okay. Now how to connect it as an auto transformer with this voltage rating? Okay, so basically auto transformers have only one coil, so we have to join these two coils into one. Okay, and how to join it? We will join them in series, but now how to connect them in series? Can I connect them like this? Okay, so that means I have connected plus minus followed by minus plus. So how much will be the resultant voltage between terminal A and B at a particular moment? So that will be 2200 minus 110. Okay, but that's not what we want. We want 2310 volt, which is basically summation of 2200 and 110. So what we have to do is Okay, maybe I do it here. So I connect it like this. Okay, so plus minus plus minus. So now how much is the voltage between terminal A and B? These two voltages will get added. The voltages are in series addition. Okay, so now if I apply okay, let me make it cleaner. Okay, if the voltage, if this voltage is 2200 volt, okay, then the voltage between this, let me call it A, B, C, D, then between A and D, how much will be the voltage? Okay, so between A and D, the voltage will be 2310 volt. Okay, so then therefore terminal AB is the primary side of this reconnected auto transformer with 2200 volt voltage rating, and terminal AD is the secondary side, other side of this auto transformer with voltage 2310 volt. Okay, is it fine? Okay, so this is one way of doing it. There may be, you may also do it in different ways. For example, let me I could also connect, say, this end here with this end, and then I can take the output between B and so let me erase this previous one. Now between B and C, how much is the voltage between C and B? Again, the two voltages are added here, 2210 and then 110. So this voltage is 2310 volt. Okay, is that fine? So this is how we can connect this two winding transformer like an auto transformer. And now the question is how much kVA this new connection, this auto transformer can handle. Okay, so before that, if I call this current as I1 and suppose this current is I2, okay, how much was the maximum permissible value of I1? Max value of I1. Okay, so this was originally a two winding transformer with 100 kVA rating and this voltage rating. Okay, so what was the maximum allowable current for the primary coil? That was 10 kVA by S, 2200 volt. Okay, how much is this? Could you please calculate? I think this is around 4.5 ampere. And similarly, maximum value of I2, maximum permissible value of I2 in this coil, that will be 10 kVA by 110 volt, which is approximately 91 ampere. So this much current is allowed at max. Okay. Now, after this reconnection, okay, now here if I put a load, how much kVA can we transform to this load. Okay, so maximum load kVA of the auto transformer that will be this load voltage 2310 volt. That's the maximum voltage we can have here, multiplied by how much current can this load have, that is same as I2. Okay, this same current I2 flows here, so that is 91 ampere, and which is equal to approximately 210 kilowatt. So that means now this load can get 210 kilowatt. Okay, so that much, so that much kVA can be handled. Okay, we may also look at what is happening on the source side. Okay, so let us see max source kVA. Okay, so here how much current can we have? That is I1. Okay, but actually it will be easier, better visible if I, instead of connecting that here, if I put it here, basically the same place, but now we will be able to see the difference better. So now here this current is, I mean the coil current can be maximum 4.5 ampere, but I may pass more current through this other path, so this source current can be more than 4.5 ampere. Okay, so now how much can the source current be? Achha, now this current, this one can be maximum I2, that is 91 ampere. Okay, so here we have 91 ampere plus 4.5 ampere, so that means maximum source current can be 91 plus 4.5 ampere, and source voltage is 2200 volt. So that will again be 210 kilo. Oh, sorry, this is not watt, kVA. Okay, so again you see that larger amount of much larger amount of kVA can be transformed from source to the load, which is 210 kVA, whereas the original transformer could handle only 10 kVA. Okay, so that is one advantage we are getting here. But if you look at any particular coil of this transformer, okay, say primary coil, okay, how much is the primary coil kVA, or how much kVA is handled by this primary coil? So the primary coil is handling how much current? I1, that can be maximum 4.5 ampere, and the voltage across the primary coil, that is 2200 volt. Okay, so that will be 10 kVA only. Similarly, if you look at the secondary coil, okay, how much kVA is handled or beared by this, handled by this secondary coil. So voltage across this is 110 volt, and current through this coil is 91. Okay, so this is again only 10 kVA. So that means actually the coils are handling only 10 kVA, but still we are able to get 210 kVA transformed from load to source. How is that happening? That is happening because there is a direct path, this path, okay, for this current to go bypassing the coils. Okay, so that's why here we say that 10 kVA is transformed by transformer and remaining 200 kVA is directly conducted or conducted. Okay, so any question here so far? Okay, is it fine? Yeah. So the main thing to notice is that the coils are actually handling only 10 kVA. So we say that 10 kVA is the transformed kVA, but since there is direct, you see there is direct connection between source and here you can see clearly the source and load are directly connected also. Okay, in a transformer, in a two-winding transformer, there is no direct connection between source and load. I mean, if I draw a two-winding transformer, the source and the load, they are completely isolated. There is no direct connection, but here there is a direct connection. So there is possibility of direct conduction of kVA. Achha, next, one more thing. So one advantage of an auto transformer, okay, so consider, so an auto transformer has only one coil. Okay, so suppose these are the primary side and the secondary side. And now what is the turns ratio of this primary and primary to secondary? Okay, if this part is small, then turns ratio will be almost close to 1. Okay, so suppose this is N1 and this is N2. Here N1 is slightly larger than N2. So suppose N1 by N2 is close to 1. I mean slightly, let me write close to 1. Okay. Then if this current is I1 and and the dots are like this, if this current is I2, how much current is flowing in this common portion? Okay, current in common coil portion, that is I1 minus I2. Now since and I1 by I2 is equal to N2 by N1, so this is close to 1, therefore this is close to I mean it's a small number. Okay, it's a small number. Therefore this common portion does not require to handle large amount of current, and therefore we can use very thin, narrow winding, narrow coil, narrow conductor, thin conductor, because the current is small. So we can use thin conductor in the common portion. Thereby we can save a lot in the cost of copper that is required to make the winding. So that is one advantage of auto transformers compared to a two winding transformer. If I have a two winding transformer with the same voltage and current rating, that will require more amount of copper. Okay, so I will not go into more detail, I mean how much copper saving is actually done. If you are interested, you can see in the notes. Now, but on the other side, let me also talk about a disadvantage of an auto transformer. Okay, suppose I have a two winding transformer, okay, and suppose N1 is much larger than N2 for this, and now I take an auto transformer with the same N1 and N2. Okay, so this is N1 and this is N2. Okay, so basically this is a step down transformer, and we are lowering the voltage by a lot, I mean significantly. Now here I have the source and here I have the load. If by any chance, say this winding breaks, the coil breaks here, then what will happen to the load? If winding breaks, what will happen to the load? It will not get any further power supply, but it will not also get damaged. So voltage across it will not be large. I mean, will not, there won't be anything. Okay, so the load will just turn off, but it will not get damaged. Okay, so if winding breaks, there is no damage. But now you see what happens for an auto transformer. Suppose here there is a break. Okay, now if the winding breaks in this region, and here I have the source, here I have the load. Now this part is gone, so I let so this part is broken, okay, disconnected. Okay, now what happens to the load? How much voltage the load experience? Okay, the load voltage will be equal to the source voltage. There is a direct connection now, and the load will get immediately damaged. Okay, so the load voltage will be huge. Okay, assuming that N1 is much larger than N2. So that's a problem. Under such situation, we should not use auto transformers. Okay. Also, one more point I want to mention is that so in laboratory you might have seen an instrument called Variac, that is basically an auto transformer. So here I have a coil, and then let me put a winding on top of it. Okay. And now let me give here a supply. And I will take output, say, from here and here. Okay. So this is the output. And now I can turn this knob and connect this jockey to different places. This is just like a rheostat almost. Okay, and so by doing this, I can actually get a variable output voltage as I change this knob position. So that's called a variac or variable auto transformer. This is quite useful in laboratory and elsewhere. This is also called Variac. Okay. Fine. Any questions so far? Yes. Okay. So, if so, then next we will take up some topics which will be more involved, and I request your patience and attention for that. Okay, so we will, look at eddy current loss and hysteresis loss in a transformer in much more detail. Okay, acha. So first let's talk about eddy current loss. Okay, acha. Suppose I have a core like this, okay, and then I have a coil and suppose supply is given here. I am not drawing the secondary coil because I need some space for drawing other things. Now we told you that this transformer is this core is not made in a single piece. It is made up of many small slices. We call them laminations like this. This is one slice. Okay, and so on. There will be many more. Okay, so let us consider one particular slice, and I will draw it largely. With a large thickness. Okay, because I have to draw something. So otherwise, these slices are as thick as a fraction of a millimeter maybe. Okay, but because I need some space for drawing, so consider a large slice. Okay, and then consider one chunk from it. Maybe this chunk you consider. Okay, just consider this particular chunk. Okay, so let me draw that here. A zoomed in view I want to draw. So maybe I make it thinner. Okay, so this chunk is shown here by a significant amount of magnification. Okay, now flux lines are like this. Okay, so here also the flux lines are like this. Okay, so and now how, and this flux is varying. Sometimes it's downwards, sometimes it's upwards, because the original current is sinusoidal AC current. So this flux will also be varying, sometimes upwards, sometimes just downwards, increasing and decreasing. So therefore we will have some eddy current generated, which will, how will that flow? That will flow surrounding around this block. Okay, and we want to estimate how much is the power loss due to this eddy current. Okay, now so basically the paths for the eddy current will be closed loops like this. Okay, there will be many more loops, and you may think of these small tracks through which current is flowing. Here we have some current, okay, and then here we have some current. Okay, so we are basically looking at it from bottom. Okay, so we are looking at it from the bottom, and this is how the eddy currents will flow. Now one thing you have to notice that this thickness, okay, this thickness is basically this thickness. So this is actually shown quite larger. Actually they are very thin, fraction of a millimeter. So this is actually very thin, but here I am drawing it quite large. Actually very thin, this particular dimension. Now how much? Now we will estimate how much is the power loss due to these currents. So for that we will first estimate how much is the induced EMF in any closed path. Then we will divide that EMF by the resistance of that path, so that we get the current, and then we will take I square R to get the power loss. Okay, so for that let me name let me just label this this as say H. This height is H, then this dimension is suppose W, and the other dimension, suppose that is tau. Tau is the thickness. Okay, so tau is very thin. Now the midpoint of this thickness, let me label that as x equal to 0, and then you measure maybe x in this direction. X is plus, and in the opposite direction x is negative. Okay, now consider this middle track. Okay, so let me dark out all the other tracks. Okay, so this track do not look at, this track you do not look at only this white track through which current is flowing. Okay, and suppose this particular track is from minus x to plus x. Okay, so this line is at minus x, and this line is at plus x. Now the first question is, how much is the flux going through this through the interior of this track? Okay, so flux, that means these flux lines, how much is the flux? going through the inside of this track or this loop. That flux I can write as flux density, that will be a function of time of course, flux density in core, multiplied by the area inside this this loop, inside this white loop. Now who can tell me how much is the area inside this white loop? That means, yes. Your voice is not coming clearly. Okay, fine. So the yeah, please mute yourself. Voice is not coming clearly. So the area is basically the length of this is approximately equal to W and multiplied by 2x. So this is the flux going through the inside of the track. Now if I take the time derivative of that, okay, that will give the EMF induced along this white track. That is the EMF. Now how much will be the current? Okay, so for that we need the resistance of the considered track. How much is the resistance? Okay, so resistance will be equal to rho L by A. Rho is the resistivity of the material, and length is how much? How much is the length of this path, this track? That is approximately 2 into W. 2 into W is the length. I mean, to be more precise, it is 2 into W plus 4x, but x is small. Okay, assuming x is small, I ignore it and write it as 2 into W. That is the length, and now divided by the area of this current path. Now this is tricky. Okay, so can anyone tell me how much is the area of this current path? Anyone? No? Okay, so let me just tell you. So that will be the thickness of this track. That is okay. If I call this, I need a different color. Okay, so okay, let me zoom in this part once again. Okay, and draw it here. Okay, so we are considering a narrow track okay, so this side is at minus x, this side is at plus x, the midpoint is x equal to 0, and this thickness is say dx. Okay, so then dx into this h is the area of the path of the current, and cross-sectional area of the current path. Okay, so that's the resistance. Okay, so now how much will be, so we have the voltage, we have the resistance. Now how much is the power loss? So power is basically voltage square by resistance, so that will be so dB dt, this dB dt into W 2x square of that voltage square, so let me make it 4x square, okay, divided by the resistance is rho 2 omega, and this dxh, let me write above, h dx, dx or delta x. Okay, so that's the power. Now this is the amount of power being dissipated in this one track. now you have to consider all other tracks. For example, if I draw here, there is another track, okay? So this is one track, okay? After that, this is another track. So there are so many paths. So for that, what do I have to do? So the total power, let me write here, will be basically integration of these powers for different tracks at different distances x. Okay, starting from x equal to 0, and how much can we go? This will be tau by 2. This will be minus tau by 2, because the thickness of this lamination is tau. Okay, so this thickness is tau. So we have to integrate it over x from minus tau by, from x equal to 0 to x equal to tau by 2, integrate this quantity dB dt whole square into omega square 4x square. Let me write h first, h, then 4h, then x square dx, and divided by 2 rho omega. Now if we integrate, we will have dB dt outside the integration. This does not depend on x. Omega square, sorry, this is not omega, I mean, let me call it w. This is not, I was constantly saying omega possibly. I mean w is this w width. Okay, please don't call it omega. Omega will have a different meaning. Okay, so this w, I mean here, w is for width. Extremely sorry, this is not omega. I mean everywhere this is w. W is the width, this width shown here. Okay. Acha. So dB dt square omega square 4 into h divide. So this will become 2 divided by rho w. Rho w. So this w and this w square I can make it w, and x square, when you integrate, it will become x cube by 3, and now you put the limits tau by 2, so this will become tau by 2 cube. Okay, so then this is dB dt w 2h by rho, and then this will become 8 into 324, so this will become 12 tau cube. Okay, now here I have a square. Now this is equal to dB dt whole square, and then consider wh into tau. Let me write it as tau square into wh tau, this quantity. Now what is this quantity inside this bracket? wh into tau. Let us see, wh and tau. So that's the volume that we are considering. Okay, so this becomes the volume under consideration. So therefore, power per unit volume of the core, that will be dB dt whole square tau square by 12 rho. Okay. Achha. Now one thing you notice, that this depends on tau square, the thickness of the lamination. So if we take thin lamination, we will have less power loss. We will have low power loss. That is one observation. Secondly, what is this rho? Rho is the resistivity of this material, the core material. Okay, so if the resistivity is higher, power loss will be low. So if resistivity of core rho is high, loss will be low. That's one thing you can observe. That's why we use thin laminations having small values of tau. Achha, now let me finish this further. So now dB dt whole square is how much? Okay, so suppose this voltage is sinusoidal, and therefore the current is also sinusoidal, and suppose for that the flux density is also sinusoidal. Okay, so suppose B is equal to B max, the amplitude, some amplitude, into say sine omega t. So here this is omega. Okay, this omega is the frequency of the supply. That will also be the frequency of the flux variation. Okay, so then how much is dB dt whole square? That will be, so if you take the derivative, you will have a omega coming out. So you will have B max square omega square, and the derivative will make the sine into cosine, cos square omega t. So this term is also a function of time. Now, how much is the average power? Okay, let us calculate average power. For that, so let us calculate time average of dB dt whole square. How much will be that? So B max and omega, these are constant. So B max square omega square, those are constant, and cosine square omega t is varying with time. So let us find the average of cosine square omega t. But do you know how much is the average value of cosine square? Half. Excellent. So that's the average value. Excellent. Okay, so therefore average power loss, average power per unit volume, that will be, so let me put this value in this expression here. Okay, if I put it, so I will have this term B max square omega square by 2. I think I have missed some coefficient somewhere. No, yeah, tau square by 12 rho into tau square by 12 rho. You may also write it as B max square. In place of omega, we can write 2 pi f. So 4 pi square, f square, tau square, and below we have 24 rho. And okay, let me simplify this and make it 6. That's the expression of eddy current loss, power loss due to eddy current per unit volume of the core on an average, I mean time average. Okay? Achha. Oh, now one thing you should observe here. So now observe that for a transformer, if this voltage is V, call it V1, okay, then we know that V1, RMS value of V1, okay, V1 is given by, that is a formula, root 2 pi phi max f into n. So you observe that V1 is therefore proportional to B max. Okay, because B max multiplied by core area is phi max. So V1 is proportional to B max, and therefore from here we can write eddy current loss, I mean power loss per unit volume, that will be also proportional to V1 square, I mean supply voltage square, because B max is proportional to V1. Now, this should ring a bell in your mind. This is what we should expect. Otherwise, there is a problem. Why? Because let us go back to our equivalent circuit. Okay, so here we have an equivalent circuit, or maybe maybe we look at this. Okay, now say how much is the eddy? I mean, how much is the core loss? According to our model, core loss is this V1 square divided by R0. That's the core loss, and eddy current loss is one type of core loss. So we should have eddy current loss, proportional to this voltage square. Otherwise, this model will not work. Fortunately, we have that. Fortunately, in this derivation, we see that eddy current loss is actually proportional to V1 square. Otherwise, our previous model, our equivalent circuit was wrong, if that was not the case. But here we are lucky, our model is good, our model is fine. Okay, so is there any question so far? No? Okay. Yeah. So next we will talk about another very intensive topic, which is hysteresis loss. But I think you may like to refresh your minds for maybe about 4 or 5 minutes before we can dive into another intensive topics. Okay, so let's take a small 4 or 5 minutes break. Okay, so let us begin once again, and now we are going to discuss about hysteresis loss. What is hysteresis loss? Okay, we have a core and some magnetic material, and this is made up of many small tiny magnets, north, south, okay, etc. And when we have a alternating supply here, then the flux direction changes, and therefore continuously these magnets will have to reorient themselves in opposite directions. Okay? This will happen 50 times a second if the frequency is 50 Hertz, and for this to happen, for these molecules or atomic level magnets to reorient themselves, among all obstructions, there will be some work to be done, or some energy is required continuously to reorient these tiny magnets again and again. Okay, and the energy lost in the process of orienting and reorienting these magnets is called the hysteresis loss. Now, when we talk about the property of a magnetic material, we often draw a graph which we call a BH curve, where x-axis represents H, magnetic field intensity, and B is the y-axis, that's the flux density, okay, where H is basically approximately Ni by L, where I mean this I is this current flowing through this coil, N is the number of turns, and L is the length of this core, okay, I mean the length of the path of this flux, that is L, and B is the flux density through this core. Now, as we increase current, H increases, simultaneously flux density also increases. So we have a graph like this, and this graph is quite stiff, I mean almost vertical initially, because with a small amount of current or a small amount of H, we can get a significant amount of flux density. So therefore this graph is quite steep, the slope is very high. But then what happens after some time? If I keep increasing this current, this will not increase at the same rate forever. Rather, after a while, this increase will become will almost stop. Okay, this will become almost horizontal, almost flat, because at that moment all the molecules are already aligned and there is nothing left to be aligned anymore. Okay, so even if I increase current, there is no more molecule left to be aligned, so flux density will not increase much. It will increase as much as it would have increased even in air or in vacuum. So at that rate it will increase. So the graph therefore looks like this. It will be a smooth one, and this part is called the saturation part or air line, and this initial part is called the linear region. Okay. Now, this graph is also not the complete picture. What happens if I vary this current as a function of time? Okay, so suppose this current is varying sinusoidally. So x-axis is basically proportional to current. So if this is my time direction and this is the current I, and this current is varying, how will this flux density vary? Okay, you may extend this graph symmetrically in the negative, along the negative side. But now, when I am varying this current, repeatedly very fast, then will the flux density vary along this graph, along this line? No. What happens? There is a delay between the reorientation of these tiny magnets and the time when the current is changed. If I change this current suddenly, the tiny magnets cannot reorient them instantaneously. They need some time to get them reorient. So therefore, what happens actually, this graph will look like this. Okay, let me draw with a different color. Yeah, so I am increasing the current. So here you can see, okay, so at this point current is positive, but there is no flux yet, and I have to wait for some time for the flux to be generated. Okay, and then here also you see the current is already negative, but flux is not yet negative. I have to wait for some time for the flux to become negative. So there is a delay between the reorientation of tiny magnets and the change in the current. So this graph is called the this red one is the red graph represents the dynamic or time varying nature of the flux and B and H relationship. Okay. Okay, so now we want to estimate the amount of power loss due to hysteresis. So just consider only one coil. This current is I. The voltage across it is say Vt plus minus. Okay. How much is V? V will be equal to, the voltage will be equal to N into d phi dt. That will be equal to N into phi is equal to area into flux density. So A into dB dt. A is the so A is cross sectional area. L, this L is core length. So this is the voltage. So now power, that will be V into I. Okay, and so that will be N A dB dt into I. Now in place of B, in place of I, let me write I will be HL by N. HL by N. So these two N's cancel. Okay, so this is the power. So energy, that will be P into dt, power into dt. You can integrate to get overall power or average power maybe. Okay, okay, so yeah. So this will be then equal to AL into HdB. Okay, by dt and this dt. So this 2 dt will cancel. Now this is integrated. Now A into L, area into length, that is the volume of the core. Volume of core multiplied by H dB. B is function of time, so H is also function of time. So that we have to integrate. Now let us look at this term H dB. Okay, so let me write here. So we want to find this integration H dB is how much. So in this graph, at any particular moment, suppose this is the point representing the flux and the corresponding magnetic field intensity. Okay, so then this is H, and now as time progresses, current changes, and therefore I move from here to here. I say move from at this point to this point. Okay, so this will be dB. Now H into dB is basically the area of this strip. Now I am integrating this quantity H into dV over time. So as I move further, I come here, then H into dB will be the area of this strip, and then I come here, now the area will be, so I will have the area of this strip, and I am adding them up, integrating them up all. Okay, so I come here, but after this point, now I am coming backwards. And when I am coming backwards, dB is negative. And if dB is negative, now this area will be negative. So this blue area will get cancelled from the previous one. Okay? And in this way, if I keep adding it, what will I get finally after one complete cycle? I will get the area inside this BH loop. Okay, so therefore this will become, okay, so this is integrated over time. So this will be finally become this core volume into integration of HdB integrated over time will be equal to area inside BH loop multiplied by number of times we traverse the loop in the given time. Okay, so therefore I can write that energy per unit volume per unit time, that will be equal to area inside BH loop, or you may also write so energy by time is power, so I can write hysteresis loss, hysteresis power loss per unit volume is equal to the area inside BH loop. That means basically which area? That means this area. You see this area. Now one empirical formula or experimental formula is that this hysteresis loop, this hysteresis loss is proportional to B max, maximum flux density, whole to the power 1.6. Okay, so what is B max? B max is basically this maximum flux density. Okay, so larger this B max is, the hysteresis loss will be more. Okay, now yeah, here one thing I can tell you. Okay, suppose this is a BH plane and I first draw the BH graph for a small value of sinusoidal current like this. Okay, and then I take a larger value of sinusoidal current and draw the graph. Now it will be like this. Okay, so in the second case, the current is, how much is the current varying? It is varying from here to here. So current is varying more. H is proportional to I current. Okay, and in the previous case, how much was the variation of current? That was from here to here. Okay, now if I suppose this green current is twice as large as this black current, I mean the amplitude of the green current is twice that of the black current, then what, so the width of this graph is twice. Now will the height of this graph, so this height, this is the, so this height will it also be twice that of the previous height? That means this black height. Will it be twice? No, because of the saturation phenomena, even if we increase current, the flux cannot increase that much. Flux increases by a smaller extent. So the height of this graph will not be twice if the width of this graph becomes twice. If both of them were twice, then what would have happened to the area of the graph? Then the area of the graph would have been 4 times. That means the area would have been proportional to current square. But since flux cannot increase as much as the current, therefore the area will not be proportional to the current square. Okay, area is rather less than that. So therefore the hysteresis loss or area, this is not proportional to B max square. That would have been the case if there were no saturation, nothing like saturation. But due to saturation, this is less than power 2, this is 1.6 here. Okay, so this is not the case. We have B max to the power 1.6. Now, one thing you observe, supply voltage, this voltage, okay, if this is, if this is V RMS, okay, then let me call it V1 as I called it previously. Let me get some space. Okay, suppose this is V1, then we previously told that V1 is equal to root 2 pi phi max, so that means B max into area into n into f frequency. Okay, so V1 is proportional to B max, but hysteresis loss, that is proportional to B max to the power 1.6. So therefore, this is not proportional to V1 square. So now, what do you think? Is our equivalent circuit model perfect? Is this model perfect? No, it's not perfect, because if this, according to this model, core loss should be proportional to here, or you look at this diagram, core loss should be proportional to supply voltage square. But hysteresis loss, which is one part of core loss, that is not proportional to supply voltage square. Therefore, this model is not perfect, and this model will not work well for different supply voltages. If we are using it for one particular supply voltage, if the supply voltage is constant, then okay, we can adjust the value of this resistance so that that models the hysteresis loss well enough. But that particular value of R0 will not work for a different value of V1. Okay, so that is one problem here. Okay, so any questions so far? Yeah. So suppose I give you a problem like this. suppose this is G10 ohm, and suppose this is also say minus J10 ohm. Okay, solve this circuit. How will you do that? Okay, so find out. So these are phasors, so let me specify angles. If not specified, then you can take it as 0, no problem. Oh, what is missing here? Otherwise, you cannot solve. A very important thing is missing. Dots. Suppose, okay, let me make it complicated. Let me put the dots like this. Okay, so find out everything. Say I1 is how much, what else, I2, or okay, then maybe this voltage. How to solve this? Yeah, these are phasors. Yes? No idea? Fine. Okay, one way to do this is to transform the primary circuit to the secondary side, or the secondary circuit to the primary side. Either way you can do it. Okay, so suppose I transform the secondary side circuit to the primary one. Then what do I have to do? I keep the primary as it is. This is 100 angle 0 degree. This is J10. Okay. Now the secondary is brought to the primary side. So what will happen to these impedances? This will become minus J10 into N1 by N2 square. So 1 by 2 means half square. And then we have the current source. What will happen to this current source? Anyone? It will
by minus.
It will become into trans ratio is 2 by 1. Okay, so am I correct? This side to this side, 2 by, yeah. Right. Okay, so now next what? And the dots were here. So I had a dot here and the dot here. Now I have to connect it. Okay, so, but I have to connect dots with dots, so that means I have to connect it like this. Okay, or you may just flip this right side upside down, so then the diagram will be cleaner. So if I do that, then this arrow should go downwards. This dot comes here. The capacitor, if you flip it, nothing happens, and like this. Okay, so and now, now how much is this current? Who can find it? Which method will you use? Say, you may use superposition. I think you can use superposition. So I1 will be how much I1 will be due to the voltage source. If this current source is not there, that will be 100 volt divided by J10 J10 minus this is 2.5.
2.5.
So yeah, this is the current due to voltage source, plus how much will be the current if this voltage source is not there but this current source is there, then that will be so this is 4 ampere. So 4 ampere, this 4 ampere comes here and then it has two paths. Okay, so apply current divider. So we will have minus J 2.5 divided by the sum of these two is J 7.5. Am I correct? And now you can simplify it. Okay, so this is 100 by J 7.5 plus this is 4 by 3 minus 4 by 3. Okay, please check, am I correct or not? Please
There will be minus
where?
in the middle for that plus after the first term, because for the current source the current will be negative opposite
So
direction.
this current is flowing in this direction, in this direction. So part of it goes here, part of it goes here. Okay, so this is in the same direction as I1, na? So that's why just 4 ampere, and this minus is coming because of this minus J. I think it's correct. Can somebody else check and verify? Okay, okay, you can check it later. So you will get the value of I1. Achha, now, so we got I1, and now how much is the voltage here? From here to here. Okay, let me call it V2. I cannot call it V2 because V2 is already used here. Let me call it V2 prime. Okay, so how much is this voltage? So V2 prime will now be I1. So I1 comes here. Here is I1, and here is minus 4. So this is I1. And okay, what am I taking the direction of V2? Suppose like this, plus minus. So capacitor current is I1 minus 4 into minus J 7.5 ampere ohm. So you can get this value. How much is this? Oh, this is V2 prime. Okay, fine. Now, so that is in this circuit. Now, what will be the solution of the original circuit? In this black one. So this I1 will be same as this I1. But what else? Achha, now this I2, how much will be this I2? Okay, here we have the current I1 flowing here. So how much will be this I2 in the original one? So this, so this will be this I1 minus of that because this is in opposite direction. Okay, maybe I call it I1. So this is I1. So this will be wait. This there is one more thing. This I2, we have also flipped this diagram upside down, right? So this I2 is actually this I2. These two are same I2, and therefore, so this is the current coming out from the dot. This I1 is also coming out from the dot, so they are in the same direction. Okay, so therefore this will be I1, this I1 multiplied by, what should I multiply this with? Okay, so you recall that we multiplied by 2 when we drew this red circuit. Okay, the currents were multiplied by 2, so now I have to multiply by half, reciprocal of that. Okay, so I will get the value of I2, and then what will be the value of this V2? This V2 will be this voltage V2 prime multiplied by what? Okay, so to go from here to here, we multiply voltages. We should multiply voltages by half. So now to go from this circuit to this circuit, voltage should be multiplied by 2. So this will become multiplied by 2. But that's not all. One more thing. Here you see this plus is towards the bottom side of the current source, but here this plus side is towards the tip of the arrow of this current source. So therefore, we should also have a minus. Okay? Yeah. So any question here? This prime.
Sir, why I2 is not and
Your voice is breaking. Could you please write or try once again?
Sir, is it audible now?
Yeah, now audible.
In I2, why we didn't multiply with -1?
Yeah, because this I2, the original I2 was this I2, na? That was the current which was coming out from this. Okay, it may be better if I just give some names, like call this A, B, C, D. So now here I have A, B, but C and D are reversed. C, D. Okay, so I2 is the current coming out from D. Okay, and here also I1 is the current coming out from D. So they are in the same direction. So that's why we don't need a minus sign.
okay, sir.
Please check whether I have done any mistake or not. It's completely logical, but I might have done some calculation mistake. That you should check. Okay, fine. Maybe one last question we can take is this. Okay, suppose I have 3 transformers. All ideal. Okay, and they are connected, and suppose this is 1:2. Suppose this is what can I take? 2 is, let me take 1:2, okay, for simplicity. Okay, or 3:2. And then and suppose the dots are like this. And these are all connected in this way. It is safer if I put the dots here. And like this. and this. And somewhere there should be at least one supply, otherwise it will not do anything. Okay, suppose this voltage is given, plus minus 100 volt. And okay, now in this circuit, Achha, could you tell me what should be the turns ratio of this transformer, which will not create any problem? What should be the turns ratio of this transformer, which I haven't written? Yes? Okay, maybe it will be easier for you if I put this source here. Now tell me what should be the turns ratio of this this third transformer.
It will be 1
1 is to 3.
1:3, right? Okay, so I may put here also one more source. What is the safe voltage for this source? That should be 1 to 200.
3.
No, 300. Yeah, 300. And if I put one more source here, that should be, okay, I mean these are all with angle 0 degree, same phase. What will happen if they are not in same phase? This should be 200 volt. What will happen? So then as if that will be a situation similar to if I connect two different batteries face to face with different voltages, 12 volt and 10 volt. What happens? That's a disaster. Okay, so if there is no resistance in between, that's a disaster. So therefore, these voltages should also be in this ratio, 100, 200, 300, and they should all be in same phase. Okay, but let me put, before that, one more thing. Can I put these dots here? Will it work? It will. It's basically the same. You know, I mean, when I put these dots here, I mean, then it means if I name them as A, B, C, D, then it means that voltage polarity wise A is same as A is similar to C voltage polarity wise, and B is similar to D. Okay, A similar to C means B is also similar to D. So there is no harm in putting two identical symbols to D, to B and D. I can also now remove these two. The same meaning, I can also put the dots here. The meaning is same. Okay, but now can I put one dot here and another dot here? No, because now what happens? Okay, so the moment when say this voltage is positive, so say at that moment, so this dot is positive, so this dot will be positive. I mean with respect to this is minus, minus, minus. So at that same moment, so this dot is positive, this dot is positive. So that means this is negative. That means this C is negative, D is positive, and C is now identical to B according to the dots. So here I will have minus, here I will have plus. Now you see I have a short circuit here. This plus is connected to minus and this plus is connected to minus. So there is a short circuit. Again, two different voltage sources are connected face to face. So this is not allowed. I should have this dot here so that this is minus and this is plus. So this is okay. Okay? Fine. Now I will just give you one question and leave that as homework. Okay. Let me put some impedances. Okay, say some resistance I just put. The simplest thing is the resistance. Okay, suppose this is given 10, yeah, so this is 10 ohm, okay, and here suppose I put one resistance which is 40 ohm, okay, and then here I put a resistance say which is 90 ohm. Now you have, I may put more resistances, maybe here one more 10, or let me make it 20, okay, okay, let's keep it 10 for simplicity. Here one more resistance 40, and here one more 90 ohm. Okay, how to solve this circuit? The basic idea to use is that we have to transform these different parts, like suppose this is one part of the circuit. Suppose you keep it as it is, keep same, unchanged. Then you say consider another part of this circuit. Okay, this we want to change the voltage, currents and impedances by some factors so that we can connect this directly to the orange one, and then say this one okay, change it so that we can connect them together. Okay, so what can we do? Maybe one possibility is that here we multiply voltages by half and resistance by half square. Okay, for this you multiply these voltages by 1/3 and resistances by 1/3 square, 1/9, and then you connect all of them together. Okay, so then you connect this to this, this to this, then this to this, this to this, okay, this to this, this to this. Forget the presence of the transformers and just solve the circuit, and then scale back the voltages and voltages to get the result for original circuit. I leave it as a homework.